Hi everyone. So I'm Yoshihiro Nakajima from NTT Laboratories. So I'm very happy to introduce our work of the high performance software switch of the user, by the user, and for the user. Okay, so this is the agenda of my talk. Basically, I shared some background of the vSwitch, and also I show you our design and the concept and the implementation of our high-performance software switch. Also, we will demonstrate later some use case of the carrier systems, segment routing system from Ishida-san. Okay, our mission is to innovate networking area using the open source technology. So we think that open source is a very essential part for SDN and NFP. We try to provide the very good or great software switch for industry and networking operators. Okay, first I introduce some background and the motivation of this work. As you know, we are in the big changing point from traditional way to provide a networking for customers from new rapid and very complex way to provide a networking for the users. As you know, so sorry. Oops. Well, basically, everyone loves open compared to the closed system. Also, the development cycle is much faster than ever. Also, the commodity hardware and the commodity software is very good for us to provide or develop our network service. And we think we try to make forward this movement for the networking area. So one question for everyone. So do you know SDN? So please raise your hand. Oh, very good. Okay, I will introduce the SDN briefly. And basically, SDN is to try to decouple the control system and the data plane, and also it provides logical centralized view for customers and users and administrators. Also, it provides a very programming model for everyone. So that is a very convenient for us to develop the new network services, because the legacy system, basically, it is difficult to manage the many vendor variety nodes. We think this movement is very key for next generation's carrier system. And we think this movement is much similar to development of the software side. Okay, this figure shows the comparison between the legacy system and the OpenFlow system. To achieve the high availability and the high performance, so the legacy system is basically vertical integrated. In the other hand of the OpenFlow system, so there are two main components. One is a controller, and the other one is a OpenFlow switch. And basically, OpenFlow switch includes many flow table, multiple table to realize a flexible programming for flows. And one of the interesting feature of OpenFlow 1.3 is that supports a multiple table to realize the flow processing. We think this feature is difficult to realize using the hardware-based switching. Okay, we think it is important to evaluate the benefit of the SDN by implementing our controller plane and switch. And basically, this talk is mainly for switch side. And Ishida-san will present the control plane side using our switch. And as you know, so many presentators said, so we need much agile and flexible networking for users and operators. So that allows the automation in provisioning, operations, and management, and so on. Also, that provides the seamless networking for customers. For example, the cloud system, we try to automate some connectivity to realize the connectivity between several sites. Also, currently, many network carriers are very interested in to deploy the NFV system. But in order to deploy such kind of software-based system to real world, so we need much short latency processing, and also we need a wireless system in case of the short packet. So that is a challenge for x86 servers to realize such kind of massive packet processing in the. Also, at the start point of the this project, we could not find the good OpenFlow 1.3 software system that supports the 1 mega flow rules and also the wire rate of the 10 gig. We collected some requirements for the virtual switch from the network carrier operators and strategic. And we found some requirement of the vSwitch. First one is, so it is better to run the switch on top of the commodity x86 servers and commodity network interface card. Also, the many operators want to deploy the gateway system using the software switch to their production network between several network areas, such kind of data centers and IPVPN and MPLS system. Also, the performance is very important for us because most of the network is connected by the 10 gig NIC or 10 gig switches. Also, we need much flow rules processing in the one node. Also, some operators said, so we want to upgrade the software for the new version, but it is difficult to upgrade the software because the software basically is run in the kernel mode. It is difficult to get the support from vendors. And we think that user space switch is good for the management side and operation side. And we need some management protocols such as SNMP and other configuration protocol to realize the provisioning and automation, automatic configurations. And so many people ask me, so why do you use the x86 servers for networking? So we think that the power of the x86 server is much powerful. So also, it is easier to purchase the server all over the world. Sometimes it is difficult to purchase the good network routing system in case of the some Asia Pacific areas. And the one of the interesting feature of x86 servers is so we can configure the total memory size and the CPU clock and the configuration up to your budget. Also, the last one is the most important thing for us. Basically, we know the NPU is much powerful compared to the x86 CPUs. But so there are many programmers of x86 servers. So it is important to continue the technology for the next decade. Okay, let's move to the our software switch details. So we introduce our concept and the design and some implementation details. Also, I report some performance result. Okay. So we think that our first target of the software switch named Lagopass, it's a kind of bird. So basically, as I mentioned before, the performance is more and more important. Also, we need some support for the massive flow rules. Also, we want to expand the SDN area to wider networks. Basically, the data center networking can be managed by SDN technologies. But so there are no use case for wider network. We try to develop the good or great software switch for such kind of network areas. So in that system, so we try to implement the MPLS and the PBB protocol support. Also, we need some management protocol to operate the whole big network. Okay, let's move to the our implementation approach. So we think so simple is much better for everything. For example, to realize a high performance packet processing in x86 servers, the complex algorithm might be not good, because basically the internal logic of the CPU can detect the very simple way. So that means that if I can optimize our code in simple, so the CPU can accelerate some memory access mechanism or a cache mechanism. And also, we decided to employ the straightforward approach for OpenFlow switches. That's why, therefore, we don't support the OpenFlow 1.0. That is a very primitive OpenFlow switches. And we start our implementation from the full scratch. So we didn't refer other existing software switch. Also, we decided to implement our software switch as a user space packet processing mode. And we keep the kernel code too small. Also, we decided to, how can I say, every component can be replaced to future work, other future work. We think we can optimize the flow lookup algorithm or libraries and the protocol handling in some way, so for the future research. Also, this figure, So this figure shows our overview of this simple software switch. So there are two parts. So one is the agent part that manages the protocol and handles some OpenFlow protocol. And in the data plane side, so we try to implement some software data plane, also some ASIC support. Okay. So in order to realize the high performance packet processing in x86 servers, we try to address some issues that cause in the x86 servers. First one is the massive RX interrupts in case of the receiver side. We just use the polling mode to receive the many packet. Also, sometimes the context switching causes some performance degradations. So we try to explicit assignment of this thread to physical CPUs. Also, so there are many bottlenecks of the memory side and I/O side. We try to reduce the number of access in I/O and memory side. And last one is to realize the multiple processing of for the flows. So we try to keep some data in local and to realize the multiple processing. So we need some lock mechanism. So that causes big performance degradations. So we try to employ the lockless queue and RCU-based libraries, also the batching processing for the packet. This figure shows the difference between the legacy application of the Linux software switch and other one is vSwitch with DPDK. So as you see, we can reduce the number of memory copy by using the kernel bypass. Also, we can reduce some interrupt-based packet handling using the polling mode base. Okay, let's move to our implementation details. So from this slide, we shared some technique to realize a high performance packet processing in x86 servers. First one is how to the CPUs. Using the multi-core CPUs. So decouple the two types of the processing. One is the I/O, and other flow lookup packet processing. So due to the decouple of this thread, we can realize the improvement of data cache of the CPUs. We can integrate these processing in one CPUs, but that our experimental results shows the efficiency of the DKS caused some performance degradations. So that is easy way to realize a high performance packet processing in x86 servers. And the second one is the packet batching. Maybe to proceed some packet. For example, this figure shows the basic lookup mechanism for switches. Packet goes in and switch look up some headers of a protocol, and that in order to protect this lookup table, so we need some lock. But packet by packet locking causes many waiting time to get the permission of the lookup tree. So using some multiple can perform some multiple packet in the one simple lock. So that decreases number lock time and waiting time for lookup table. And the second one is that focused on the OpenFlow 1.3. So as I mentioned before, the OpenFlow 1.3 supports a multiple table lookup. So so this is a naive implementation of OpenFlow 1.3. So we need much flow table lookup, and so we want to decrease this kind of lookup using the flow cache mechanism. So we just employ the simple algorithm to correct the header match, and we just insert to the flow route, integrated flow route to flow cache. So the succeeding flow can be reduce the number of flow lookup table. Okay, we'd like to share our preliminary performance result. So this slide shows our performance evaluation summary. So first one, we can achieve the 10 wire rate. Also, we can support the one main flow routes in the same system. And we compared our performance using the one data center gateway system that converges MPLS network and VLAN network. And basically, this idea is this evaluation scenario is inspired the our NTT Communications use case of this SDN system. Also, we compared existing software switch using the L2 basic switching. We used the hardware-based tester to ingest the flows, and we varied a packet size, number of flows, and also throughput. And we can set up some flow rules to know the scalability of flow rule processing. In that moment, we used the Sandy Bridge-based system. And this is one data center gateway performance. And we enable the forecast mechanism. We can achieve the almost wire rate. And also, we increased the number of flow rules and real ingest flows. We can achieve the 10,000 flows. We can achieve the wire rate, but over the 10,000 flows, the memory bottleneck caused some performance degradation. But we try to improve the lookup algorithm to minimize the access to the main memories. Also, this is the performance comparison between the existing switches, Link and OBS and our software switch. Basically, in this configuration, we can achieve the 4 times faster than existing good OBS system. And to compare the user space mode, maybe more than 50 times faster than user space-based switching. Okay, Ishida-san will present the proof of concept of a carrier system using the OpenFlow technologies. Okay.
All your performance data was pretty only 2. What about the latency? Do you have any numbers for that?
Okay.
Let's say 1+1.
Okay. So are you asking the number of ports, real ports, or
Latency.
latency? Latency basically less than the existing system. But I will, in this moment, I have no material to, so I will check our latency later. Okay.
I have questions. Do you handle the flow aging? Because you support a lot of flows, right?
Yeah.
Aging issue, you know, it's maybe that you must have a lot of timers, right?
Yes, yes.
So during your test, do you start enable the flow aging?
Yes, we implemented such kind of aging timer-based system in our software switch, but it is difficult to realize the fine-grade timer-based flow processing compared to the static. So in this evaluation, we used some, how can I say, the timer-based timer inside of the, in case of the layer 2 switching. But we think our implementation can be good compared to the existing software switch.
Okay. Yeah. Also, for your performance, how many CPU core you use? Because you have I remember, for I/O you have the 1 core, and then for processing you have a core.
Yeah.
So
Okay.
We must give some core to VM.
Okay.
If you use every core for your switching.
Yeah. That's a good question. Basically, the for the layer 2 switching, we just use the total 4 cores. So in case of the data center and the one gateway system, so we use the 12 cores because the flow lookup entry is more complex compared to the layer 2 switching, and we need some processing time to proceed.
12 core for the for the switching, right?
Yeah. But this is a gateway system.
Okay. Yeah. Okay. Thank you.
Not to run VM. It's to be a data point.
Excuse me?
It's a different application of what he's talking about.
Okay.
Did you have a question? There's one more question.
One more question.
So with the OVS comparison that you are doing, like, did you have like megaflows enabled or disabled in that test?
Okay. At the evaluation, so I enabled the megaflows.
It was enabled.
Yeah, enable.
And you were still seeing like a lot of packets go to user space.
Yes.
Okay. So was it like because of the nature of the traffic, like what kind of traffic, how many, like, what kind of traffic were you sending and how much of it was actually getting optimized to megaflows?
So that is a good question, and so in our case, it is difficult to optimize the megaflow in case of the OVS. So because there are many parameters to get the match performance, and at the moment, I conduct the performance evaluation. We use the default parameters to measure the OVS performance.
Okay, so basically of the percentage of traffic that you were handling, right? Like how much of it was going to user space? Do you know, like with OVS?
Excuse me?
In the test, like what percentage of the traffic was basically going to user space?
Oh, okay. We use the basic test suite of layer 2 switching. So this is RFC 2889
I see. Okay.
model.
Okay. Thank you.
Were you using a static network topology or was it a dynamic topology? Was your network static or dynamic? The flow rules, were they changing while your test was running?
Okay. For the first scenario, so we use a static configuration, and layer 2 switching evaluation scenario, we use the dynamic topology.
Okay. Okay, so let's go to the next part. Actually, I'm Ishida from NTT, and I'm actually not in a development team of this vSwitch, and I'm actually doing development of the OpenFlow controller called U. So today I'd like to introduce the control plane of how we are going to use our vSwitch. So the use case is named Spring. How many people know Spring or segment routing here? No one? Oh, 1, 2. Okay. Spring is an alternative way of IP forwarding. This is this Spring is how can I say standardizing under IETF now, and this use labels to forward packets like MPLS, and much simpler architecture than MPLS network, and can utilize traditional MPLS routers and have a good chemistry with NFV. And why we want to use this is we want to do the policy-based routing, explicit routing instead of shortest path routing, or do some service chaining things to apply services to specific traffic pattern. Okay, and this shows our carrier network, and the blue box is represents the backbone, and customers' routers surround the surrounded round routers. And we think we can use Lagopass, our vSwitch, as an NFV server with carrier-grade routers shown here. And in the Spring network, all the routers and NFV routers can be tagged with some labels. And when the ordinal IP packet comes in from the customers here, we can assign some policy to these specific application flow and push these labels to the ordinal IP packet at the ingress routers. And these labels can be implemented using MPLS labels. And here we push the, no, I missed the color of the label, but here we, for example, we push the green label and the purple label. First, we use the green label and forward it to here and apply some NFV function and strip the green label, and I missed the color, but forward the packet to these 6 routers. Okay, and these label stacks represent the policy in Spring Network. Okay, and we implemented some simple POC using vSwitch and Liu. And this shows overview of our POC. And there are policy database. In this database, there are information which application flow should be pushed which label stack. And there are Liu and router to get the topology of the networks, and the Lagopass, the vSwitch. And below the yellow plane, there are this is a customer's routers, and above the yellow plane is a Spring network, the carrier network. Okay, so I will show demo video. Can you switch? Sure. Okay. So I can't control by this. Okay.
I think you'll have to.
Okay,
I
okay.
think it's only the little red button. I think this I usually turn off, but we have to. You know what? Hold on a second. This would be confusing because I don't have the screen. It's gonna be all right if you run it off of there.
Okay.
I don't know if you can see that or not. It'll be a challenge for your hand, but
Yeah, it's difficult.
try it this way. There you go.
Okay. Okay. This is the GUI of our POC, and the left side is topology view, and the right side shows a list of routers and the details of the routers. So you can see the router name and the packet count and byte count, and which labels is assigned to these routers. And you can see we can assign a new label here. Okay, and when we click the network, we can see which network is associated to the which router, and we can see we can add the policy, which label we should stack at the ingress router. and we start ping from the pink network to gray network. And in Spring, we enabled IP default. By default, we enabled IP reachability, so the ping is working fine here. And also the ECMP is working, so if we see, the counter is incrementing. Yeah, and we can see the packets are going in a two-way. These are blue, green, red, and destination, and blue, brown, red, and the destination, because the ECMP is enabled. So what we can do with Spring is if we want to use this link, we can add a new label to this router and assign the new policy to these two networks. And if we do so, the packets go only this route and not this route. So the counters won't increment here. And also we can do the ECMP with labels. So if we add the same value here, so the color of the label is same, the packets from this pink network will be load balanced in a two-way. So the packet will go like here and like go here. So we can do the load balancing using these kinds of labels. And added to this, since this is an NFV server, we can add the labels to the services. And we can do some service chaining things using the same methodology to the explicit routing things. So you can use same protocol. And DPDK and our vSwitch can be used here, we think. And the other routers can be the legacy carrier grade routers. Okay, my part is done. So
back to the slide.
yes.
Okay, our high-performance software switch, also the control plane library system can be downloaded from the GitHub. Please enjoy our open source software. And we try to continue the to correct the requirement of the users, and we keep our software for your future development or deployment system. And also, we need your contribution to improve the software quality or to increase the functionality of the software switch, also the control plane side. this is a summary of my talk. We contribute vSwitch development for the users. So we try to catch up the 40 gig or 100 gig performance. And also we try to implement the, how can I say, the tunnel processing for the software switch. So we need some IP stack or other more upper layer handling in software switch. And we think that DPDK is a gateway for new networking technologies. We think so that DPDK allows the flexible programming for packet and flows and control for the network. So thank you.